Have you ever wondered what holds the universe together at the most fundamental level? Well, today we're going on a journey deep into the heart of the atom itself. To find out, we're going to unlock the secrets of the atomic nucleus.
Okay, first things first. Let's get a handle on the scale we're talking about, because it is absolutely mind-bending. Picture this. If an atom was scaled up to the size of a classroom, its nucleus, that thing we're about to explore, would be no bigger than a tiny pinhead floating right in the middle. The rest is just empty space.
So right away, that brings up our central mystery. If the nucleus is that ridiculously small, but it contains almost all of the atom's mass, what is going on in there? How is that even possible? This is the exact question that completely stumped scientists for decades.
So let's start our investigation. We're going to zoom in on the properties of this unbelievably dense, tiny little heart of the atom. The numbers here are just staggering. That tiny nucleus, taking up a vanishingly small amount of the atom's volume, contains over 99.9% of its mass. To try and put that into perspective, the density is something like 230 quadrillion times the density of water. It's just absurdly packed. And this is where things get really, really weird. Because we all learn in basic science class that like charges repel, right? Well, the nucleus is crammed full of positively charged protons. So physics tells us this whole thing should just violently fly apart in an instant. But it doesn't. So why not? To figure this out, we need to know what's actually inside the nucleus. So let's meet the key players that make up this atomic blueprint. So the nucleus is made of two main types of particles, and we call them nucleons for short. First, you've got the protons, which have a positive charge. They're what determine an element's identity. And then you have the neutrons. They're neutral, no charge at all, and they were discovered by James Chadwick back in 1932. They basically just add mass. Now, the specific recipe of these protons and neutrons is what gives us different types of atoms. For example, isotopes are atoms of the same element that have different numbers of neutrons. Think of them like different versions or flavors of hydrogen. Isobars, on the other hand, have the same total number of particles, but are actually different elements.
Okay, so we know what's inside. If we just add up the mass of all the parts, we should get the mass of the whole nucleus, right? Simple math. Well, this is where our mystery gets even deeper.
Let's run a little thought experiment. We're going to build a nucleus for a very common element, oxygen-16. All we need are its building blocks, 8 protons and 8 neutrons. All right, the logic here is super simple. We take the known mass of one proton and multiply it by 8. We take the known mass of one neutron, multiply it by 8. Then we add those two numbers together. This should, I repeat, should give us the total mass of the final oxygen-16 nucleus. But look at this. The expected mass, what we calculated, is actually more than the real measured mass of the nucleus. It's as if some of the mass just vanished when the particles came together. This means the individual parts literally weigh more than the finished product. Now, this bizarre little difference has a name. Scientists call it the mass defect, and it's not some kind of measurement error. It's real, and it's a fundamental clue to figuring out what's really going on inside that nucleus. And the key that unlocks this entire mystery? Well, it's probably the most famous equation in all of physics. Albert Einstein showed us that mass and energy aren't separate things. They're two sides of the same coin. You can convert mass into energy and energy back into mass. So this is it. This is the ultimate cosmic glue. We can finally explain where that missing mass went. And in doing so, we're going to finally understand what holds that nucleus together against that incredible force trying to tear it apart. You see, the mass wasn't lost at all. It was converted into a tremendous amount of energy. We call this the binding energy. This is the energy that's released when the nucleus is formed, and it's the very same energy that now acts as that cosmic glue, holding everything tightly together. In fact, you'd have to pump that exact same amount of energy back into the nucleus if you wanted to break it apart. So there you have it. Our two big puzzles are solved. That repulsion between protons is completely overpowered by an even more powerful force, something we call the strong nuclear force. And where does the energy for that force come from? It comes directly from converting that tiny bit of missing mass into pure binding energy.
Now, this binding energy isn't the same for every element, and this graph you're seeing, the curve of binding energy, is honestly one of the most important charts in all of physics. It's like a roadmap that shows us how stable the nucleus of every single element is.
Let's break it down really quick. On the far left, you have the light elements, like hydrogen. You can see they're not very tightly bound. Then the curve shoots up until it peaks right around iron. That peak means iron has the most stable, most tightly bound nucleus in the entire universe. And after that, as you get to really heavy elements like uranium, the curve starts to slowly drop off, meaning they're a little less stable. And the shape of that curve has absolutely monumental consequences. Because in nature, everything prefers to move towards a more stable state, kind of like a ball rolling downhill. And we can release that nuclear energy by helping atoms do just that. So there are two main ways to do this. In fission, we take a really heavy, less stable nucleus, like uranium from the right side of the curve, and we split it apart. The pieces it splits into are further up the curve. They're more stable, and that difference in energy is released. In fusion, we do the exact opposite. We take very light nuclei from the left side and smash them together, climbing up the curve to a more stable state, and again, that releases a massive amount of energy. And when I say massive, I mean it. A single fission event from one uranium atom releases about 200 million electron volts of energy. Now, that number might not mean much, but it is literally millions of times more energy than you get from a chemical reaction, like burning a piece of gold. And fusion? Well, fusion is the engine that powers the entire cosmos. It's how our sun shines. Deep down in the sun's core, through a series of steps, 4 hydrogen nuclei are fused together to make one helium nucleus. But that final helium atom is just a tiny bit lighter than the 4 hydrogens that went into it. That missing mass is converted directly into the sunlight that powers our entire planet. So, when you think about it, the stability of matter, the brilliant light of the stars, and the awesome power of the atom, it all comes down to this one profound idea: mass is energy. It kind of makes you wonder, if this is what holds the very building blocks of our universe together, what other secrets are still locked away, waiting to be discovered?